Okay, so it's a pleasure to have Dr. Katherine Freese, and she will be talking about has JWST discovered dark stars? So maybe I can send you a reminder when 5 minutes are left.
So you would like me to speak for about 45 minutes, is that correct?
Yes, sure.
Great. Well, introducing myself, I was a professor at University of Michigan for a long time, but then moved to Texas in 2019, where I'm now at the University of Texas in Austin, the director of the Weinberg Institute for Theoretical Physics, which we started a few years ago in honor of Stephen Weinberg, who was on our faculty and unfortunately passed away. So in his honor, we now have an institute and we do various events. And so I do hope you check out our webpage. What I'm reporting on today is primarily the idea of dark stars, what they are, but then also there are two papers we've published. Well, one is published, the other one's in press at the Proceedings of the National Academy of Science about candidates we've discovered in the James Webb Space Telescope. And if you're interested in a review, I put that in yellow at the bottom here, which is a review of the basic physics of dark stars. Well, so let's see, can I change slides? If you can't see, you'll tell me, I'm sure.
Yes, so we can see the slides, but maybe it would be better if you can make it full screen.
The trouble is, because I have to stop sharing, you know, there's a stupid thing at the top of the laptop, so I can't.
Okay, but yeah, but it's fine. I mean, if you want this way,
I don't know. I have to,
perfect.
if I stop sharing, let me try, okay?
Okay.
Make it full screen. But then I can't share anymore.
Oh, okay.
It's either or.
Yeah, okay, so let's go back to what we have.
I'm sorry. Because it's a limitation of what I can access with my mouse. Because once I'm sharing, then I can't then I can't reach the view anymore to make it full screen. It's really annoying.
Okay, so yeah, I think it should be fine.
Yeah, I'm sorry. Okay, so my collaborators in this work, it started out with me, Paolo Gondolo, and Doug Spolyar. And since then, there's many others have joined us. This is only some of the people who've joined us. But it's always fun to say that after we called them dark stars, then I learned about this cult film, which is terrible. But anyway, it preceded us. The basic idea of dark stars now is that I'm talking about the first stars to form in the history of the universe. And they can be very unusual. And they can be powered by dark matter instead of by fusion. Now, I'm going to say this repeatedly, but it's important to say people get the idea that dark stars are made of dark matter. That's incorrect. They're made up almost entirely of hydrogen and helium from the Big Bang, Big Bang nucleosynthesis, with dark matter constituting less than 0.1% of the mass of the star. So they're made of atomic matter and powered by dark matter. Now, this is interesting because they can grow to be very large, up to 10 million times the mass of the sun and 10 billion times as bright, which has two consequences if you have such large objects. One is, the focus of this talk, we have candidates in the James Webb Space Telescope, but the other one is that once they run out of fuel, then they collapse to big black holes. And this could be the origin of the supermassive black holes found all over the place and hard to explain in the early universe. So this is a summary, and I'm going to tell you all more of the story now of how they form. They form when the universe was 200 million years old at redshifts 10 to maybe even 50 in million solar mass mini halos. So what this is these are essentially the proto-galaxies. These are the small halos that will merge together, merge until they eventually make galaxies and so forth. And what happens when you create these mini halos is you finally have the conditions for stars to start forming. And the way that happens is that you have clouds of molecular hydrogen that are finally able to collapse, trying to make stars. And the first stars form right in the centers of these mini halos where there's a lot of dark matter. And so that's the question, what does the dark matter do? I'm repeating, they're made of hydrogen and helium only from the Big Bang. Now, as this gas cloud collapses, then it pulls in more and more dark matter gravitationally, because this is a baryon-dominated thing. And as it does so, if the dark matter is self-annihilating, then the annihilation products are primarily made of things that collide with hydrogen, which means they're trapped inside the cloud of hydrogen, and essentially they heat up, they thermalize and heat up the hydrogen. So all of a sudden you have this new heat source for the hydrogen, and this heat source can overwhelm the cooling, at which point the cloud no longer is able to continue to cool and collapse, and a dark star is born. Now here's some pictures back to the formation of the first stars. This is from simulations in Naoki Yoshida. This is the standard picture of the formation of the first stars, where you have a collapsing, self-gravitating molecular cloud that collapses until eventually you reach something. In the standard picture, it gets down to 10 to the minus 3 solar masses, and then starts accreting, gets fusion going. And the biggest it can get is about 500 solar masses, because because they're fusion powered, they're hot, they can't grow anymore, there's too much ionizing photons coming off, and so forth. And so here's the collapse of the cloud. Let me show you. This is in number density. So as time goes, you move to the right as the thing gets more dense. And you can see all the chemistry that you've got to take into account of all the hydrogen and helium chemistry. Okay, so we ask, well, yeah, but if you're in this very dark matter rich environment, what happens? Now, it doesn't have to be WIMPs. It has to be some kind of heat source. But the first thing we considered is WIMPs, weakly interacting massive particles, which weigh maybe between 1 GeV and 10 TeV. Our canonical case will be 100 GeV. And the annihilation cross-section that we take is the canonical one. That's the standard one that gives you the right WIMP abundance in today's universe, if you have early annihilation in the early universe. And it's the same annihilation that gives observable signals in people are searching for in a variety of telescopes. So this is standard stuff, standard WIMPs. And as I'll show, it doesn't really matter. You can change the cross-section by several orders of magnitude in either direction. It doesn't make any difference. The dark matter heating is it's simple. It's the annihilation rate is number density squared times cross-section times velocity. And then how much heat you get out? Well, you get whatever mass was in the form of the dark matter. So you multiply by that. And now I can rewrite this in terms of the energy density of the dark matter, that's the thing we know from simulations. And so I can write it this way. And here you can see this depends on cross-section divided by mass. We are going to try a variety of different masses, which is effectively the same as trying a variety of different cross-sections. So we're very insensitive to, as you'll see, to the differences. Now, not all of that's the heating rate, but not all of it is deposited in the gas because neutrinos escape. So we're going to assume that a third of the energy gets out in the form of neutrinos. I want to point out that dark matter, the power of darkness. Dark matter is, well, it's 2/3 efficient in the sense that most of the particle mass is converted to heat energy for the star. Fusion, on the other hand, is only 1% efficient. Only a fraction of the nuclear mass turns into energy for the star. Now, the other thing that's different is that fusion takes place in a hot central core of a star. Dark stars don't have a core. The dark matter annihilation is everywhere. Okay, these stars are cool. Dark matter annihilation takes everywhere throughout the star. We have 3 conditions for dark stars. One is you have to have a sufficiently high dark matter density. Now you're already starting out in a high density environment at high redshift at the centers of these mini halos, and then it even gets enhanced. As the cloud collapses, it dominates the potential, and it pulls in even more dark matter, which we treat via adiabatic contraction. And later on, at a later stage, we do not need this. I'm not going to fixate on this, but you can also get more if more dark matter is captured as it goes through the star when it gets dense enough. So that's a later stage. Okay, so the simulations of the first stars, this is what they look like independently of dark matter. So as time goes on, it gets denser and denser, time increasing, density increasing. This is a density profile. And we ask the question, okay, what happens how does the dark matter respond to this collapsing cloud? And let's say you start with an NFW profile, but I just want to say right off the bat, we also tried a flat density profile. It doesn't matter. It responds to the gas and the density goes up, up, up. We get the high densities we need. There's no doubt about it. Sufficiently high dark matter density, yes. Now, the second question is, as I was saying, that the dark matter annihilation, those products must get caught inside the cloud in order to heat it up. And yes, we use Pythia, the same code that's used all over the place, including the LHC, and we demanded 80 radiation lengths. So yes, these annihilation products are getting stuck in the star. And the third criterion, that the dark matter must beat the heating must beat the cooling. And so this is the curve I showed you before with all the chemistry. You move to the right as the star gets more dense. And this is the heating from 100 GeV WIMPs. When they cross is when the heating wins and the collapse stops. So I thought I'd tell you, okay, what do dark stars look like? It's very important for me to say this. These are objects, they're real stars in hydrostatic equilibrium and thermal equilibrium. They satisfy all four simultaneous equations of stellar structure, just like any other star. So what we do is we look for these equilibrium solutions, and what the solution that we find is that they have about, they're in radius, they're about 10 AU, the 10 times the distance between the Earth and the Sun. So they're big puffy objects in that sense. And they can grow to be very massive and bright, but in all cases, they still stay very cool on the surface. And that is really, really key, because that is what allows them to keep accreting, where standard POP3 early stars stop accreting because they get too hot. Now, so what we do is when they first form, they're about a few solar mass in size. Vary in the code, you vary the radius looking for an equilibrium solution, and then throw on another solar mass. Look for the next equilibrium solution, et cetera, et cetera, et cetera. The approach that we took was first to treat them as polytropes. Stars are all, this is an approximation that works basically for all stars. But then later we used the MESA stellar evolution code, the big beast, and watched the growth and evolution of these stars. I mean, you get the same answer up to factors of 2, which we don't care about. And that continues. You keep accreting as long as there's dark matter fuel, it keeps these stars cool. So you can get very large stars, and which eventually we'll talk about what that means later. But in the meantime, I just want to say that here is the density of baryons versus the density of dark matter, and you can see that the baryons totally dominate. As the star goes on, this is how bright the star is as a function of time, and the total brightness is shown in red with the different components. This is, at first, it's dominated by the dark matter, and let's say we just shut it off by hand in the code. Okay, you shut it off. All right, so annihilation goes away, and then you have some fusion kicking in. Sorry. At first, gravity, as the thing must start to collapse if there's nothing propping it up anymore, if the heat source is gone. So it starts to collapse. You get some gravity kicking in, and then fusion kicks in. If the objects are light enough, this is 1,000 solar mass one. If they're heavy enough, they collapse directly to black holes. This is kind of fun. At first, we thought, well, you have a little bit of dark matter in the center and you're going to use it up. But that's not how dark matter orbits work, as we learned from Monica Valori, who's an astronomy professor at University of Michigan. And she pointed out to me something that I was shocked, which is that 60% of dark matter orbits are very strange. They're on chaotic orbits or on box orbits, and they come back to they come to the center. Okay, so what happens is one dark matter particle comes to the center, annihilates away, provides heat, but then it doesn't matter because that one was never coming back anyhow. A different one comes in the next time. So you can really keep these things going, these dark stars. This is an HR diagram, how bright the object is versus its surface temperature. And you start at the bottom here and move up. Let's focus on these here. These are the ones that are just have the dark matter that's gravitationally in the center of the object. And so this is the 100 GeV case, and you can see it just keeps getting brighter and brighter and brighter. This is the capture case, which once you run out of dark matter for whatever reason, then you can still capture more from the outside because it starts to collapse, gets denser, you capture more dark matter. So different cases. And the capture would be a second piece. So far, we've used one piece of particle physics, annihilation. For capture, you'd need the other one, which is that WIMPs scattering off a nuclei, they lose energy and they could be captured, which is the same scattering that direct detection experiments are looking for. But we don't need that for dark stars to exist. It's a second type of dark star. All right, what happens next? Well, if they're big enough, heavier than 100,000, 150,000 solar masses, they collapse directly to black holes, which is great because there's all these supermassive black holes in the centers of galaxies. And the big one are these very early black holes that really are tough to explain. Here's a 10 to the 10 solar mass one at a redshift of 6. Blah, blah, blah. But what's even more extreme is that this James Webb Space Telescope is finding insanely heavy ones, okay? So I don't have the heaviest ones listed here, but anyway, so what we studied is that there are these distant quasars at redshifts 10 and higher that are, how the hell do you make them? If you start with ordinary small stars of 100 solar mass and try to merge them, it just doesn't work. So we have seeds. Let's say we have million solar mass seeds of supermassive dark stars that collapse to supermassive black holes. That's pretty great as far as helping out with this problem. I also wanted to mention, this is a paper we put out this week, actually, which is that George Fuller at San Diego kept saying, you haven't thought about the gravitational instability. And I always thought, that's not going to happen. Well, wrong. I was wrong. So anyway, well, what there is that these stars are teetering on instability, and if you so when you get to, there's a criterion for when you would collapse to a black hole because of this, the gravitational instability sends you over the edge. And so what we found is this is the mass of the black holes that you would get as a function of WIMP mass. It's a unique answer for a given WIMP mass. That's kind of cool. Okay, let's turn to observing the dark stars, which was the main point of the main topic for the day. Well, what do dark stars look like from the point of view of telescopes? All right, this is a very crude spectrum of dark stars, how much light comes out at different wavelengths. And the reason for this cutoff is this is the Lyman alpha cutoff. This is because if you have a distant object, there is a bunch of hydrogen in between that object and us, and that neutral hydrogen eats photons, okay? So it shuts it off at, there's a break, okay? So where it starts eating the photons. And by the way, we know the actual wavelength of the break. So by seeing where does it look, where do you see it? When you look at the object, you can figure out the redshift of the object that way. It's pretty cool. Well, how many dark stars, we don't know, but Paul Shapiro gave us the mini halo formation rate. And then actually let me back up historically, our original work was 2007. We proposed these things, and then John Mather, who was in the process of building the JWST, the Nobel laureate John Mather, said, hey, what are they going to look like in JWST? So my student at the time, Cosmin Illy, did those calculations, and that's the simple work that he did, and he figured out how many you could get depending on how many of these mini halos do host dark stars, and there could be tons out there. So we made predictions for spectra, and then when James Webb Space Telescope came along, we were ready to handle the data. Important point: one supermassive dark star can be as bright as an entire early galaxy of stars. Okay, so this is what Cosmin did. He looked, these are the filters of the James Webb Space Telescope in blue. And he looked at million solar mass dark stars, and yes, you will be able to see them. So that was the calculation he did. And again, the way you get the redshift is looking for where this dropout is because of this Lyman, the hydrogen eating the eating the photons. Oh, and here there are estimates of the numbers that you would be able to see. These would be redshift 12 objects. As you can see, depends on a lot of stuff, but it could be very many. All right, so now this is a picture of Cosmine, who's now a professor at Colgate University, working at the time with an undergraduate, Gillian Paulin. And we looked at, this is 2023, I think we wrote this paper, that at the time, there were only 5 objects in JWST data with spectra, and we found that 2 could be dark stars. We originally thought 3, but one of them now we found is not so, but of these 2 could be dark stars. These are the spectra, and there's this break I was telling you about that gives you what the redshift is, redshift 13, redshift 11. And this is new data. This is the latest thing that we've just got accepted for publication, which is, this is a new object, an object at redshift 14, and it's the most distant object ever found, could be a dark star. Pretty cool. Okay, so this is a little more detail on the spectra, but now what I want to, so what we did first is, this is in our first candidate paper, we only had the brightness in 9 wavelength bands, so this is, and so Gillian optimized and this is an example of one of the objects. So the black dots are the data, and this blue curve is the spectral fit for a 1,000,000 solar mass supermassive dark star. And this is redshift, this is redshift, very high redshift. Okay, so how can you tell the difference between a supermassive dark star and an entire early galaxy? There are several things. So one of them is if you get better spectra. I mean, if you see nitrogen, nickel, magnesium, blah, 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 that is not a dark star. It only has hydrogen and helium in it. And so the question is, how can you get better spectra? And the ideal answer to that will be finding a highly magnified object. There are finding such things. So you have a distant object with a bunch of stuff in front of it, like dark matter in front of it, and that lenses the object and it magnifies the image, and you're going to get beautiful spectra from that. So that's one thing to look for in the future. The other one is that we are predicting an absorption line in helium, the helium-2 1614 absorption line, whereas early galaxies would have an emission line. So this is a smoking gun for a supermassive dark star. So that's one thing we're looking for. Also, there is no, although there is no telescope looking at these higher wavelengths of 5 microns, but if there is, then the spectra will be different between the two. So you'll not just because of finding carbon and so on, but it'll be intrinsically different in a lot of different ways. So okay, let me say again, these were these 3 objects in the JADES, James Webb Advanced Extragalactic JADES, whatever that stands for, survey, I guess. And we found these objects that were a good fit. But now that was all spectroscopic data. In other words, you had the amount of light in each of these filters. I'm sorry, that was photometric data. You only had the information about the light in those filters, whereas now there are new candidates with spectroscopic data, which means you have much more information about the spectrum. And what we've also done on the theory side, we have more accurate spectra and estimates of the size of dark stars, because we added, in the simulations, we added the nebula around the dark stars, which is important to get that spectra to be accurate. We also did a more careful statistical analysis. And when we did that, these are the objects that we have. And these, let me just point out, these are 300 million years after the Big Bang, a scant few percent of the age of the universe. And the spectra match the data. So that is pretty cool. I mentioned the smoking gun for dark stars, a helium line. So there's a tentative signal in one of these objects, but that same object also has tentative oxygen line in there. So this is a little confusing. Do we have to reconsider dark stars forming with some elements around them. That's a new one. We haven't done that. But also these are tentative lines, and who knows which of these will persist. You know, this is an old number from when we wrote our first paper. I don't know how many high redshift objects they have now. 700 is the wrong number at this point, but the assumption is that they're galaxy candidates. But here's another interesting thing. We can solve. That hand keeps going up every time I put my hand up. Then let's see, how do I get rid of it? I'm just not going to worry about it. Okay, so there's another conundrum. Not just the existence of supermassive black holes, but the existence of these bright objects doesn't really make sense. It doesn't match the predictions from lambda CDM. Essentially, looking at just one of these massive galaxies, the inferred stellar mass is insane. Okay, so that's it's not the death of lambda CDM, which is what they thought at first, but still, it's very hard to explain. Now, so what we're speculating is that some of these objects that they think are early galaxies could instead be dark stars. So you're solving several problems by having dark stars. Now, in the future, you also have other telescopes that can look for dark stars, and including the Roman Space Telescope, which has a much larger field of view, making them easier to find. However, it does not go as high a redshift. What you can do is find them with the Roman Space Telescope and then go study them with the James Webb Space Telescope, which has much better angular resolution. And there's a paper we wrote with Sayang Zhang at UT about that. In conclusion, the dark matter can play a crucial role in the first stars. Though made of hydrogen and helium, they can be powered by dark matter heating rather than by fusion. They can grow to become very massive, up to a million times the mass of the sun and 10 billion times as bright, which means there would be great precursors to supermassive black holes. They may have been discovered by the James Webb Space Telescope. We found candidates, and we do need to find a confirmed helium absorption line as a smoking gun. That would be great. And they're also detectable in the Roman Space Telescope. Interesting also to speculate that WIMPs and their properties could first be discovered through dark stars. There's some masses of WIMPs that if you get to light enough WIMPs, then those actually would be the brightest objects, and they're very hard to discover in the underground detectors. The sensitivity that is kind of below threshold for a lot of the underground